if you have a key, you're supposed to be responsible.
It doesn't know what that word means. Maybe you should explain it.
Kind of
My
like,
plan
I
was
have a
to
key
when
to
I
baby
was working in the
chapel.
office, if no one was in there, I opened it up and I wrote my token. If I needed to use it for something,
Office of what?
Please,
my,
please do.
someone was in there and I wanted to use the microwave. Open it up, put my time down, and then I used my microwave.
I'm sure that's allowed. I've had an RA open the office for me when it wasn't open because I forgot why, but I had it or something.
Okay,
I guess you do.
another topic in the appendix that you've probably heard before, maybe even from me in other classes, but certainly has been throughout math, well, you're certain, the last few years, is the idea of function. But just kind of make sure that we're all on the same page about function. A function is a rule that we call f from one set to another set, such that for each element in the first set, there is and I'm going to change the word. I think the book may actually say unique. I'm going to change it to one and only one, because I think unique is a bit misleading. So there's one and only one f of x in B. So there's some sort of rule, maybe we know what the rule is, maybe we don't. But what makes it a function is for every input, and that's some notation here, A we would call the domain, and B the codomain. But for every input, there's one and only one output. Maybe we know how we're getting that output, maybe we don't. Just in terms of a function, we really don't have to know how the output is being done. So for me, I've got two favorite functions that illustrate this idea very well. One is what I call the gradebook function. So set A is the set of people in the class, and set B are the grades. So let's see, I could say, well, Jordan's going to see, let's see, Julianne.
We got some high expectations for you today, Jordan.
You can't tell us.
Don't make me
That'll
stress.
Krista.
A plus.
All right.
Dr. Hopkins.
Yes.
Aaron has an E at the end.
I thought she was going to say I'm going to get an A.
All right, we got two errors in this, right? Spell it right and get the grade right. Okay. My apologies. It's not the first time I've done that, I'm pretty sure.
No, but everybody does it at some point. At least it seems like all my teachers do. So.
Okay.
I was told it was one name.
Yeah. Well, your email just pulls up as Julie, and so it's like, and I think she probably wants the N with it. I don't know, but
It doesn't matter if you use the and with it when you talk to me. I just.
But if you're going to use it, spell it right. Is that what you're telling me?
Exactly.
Okay. And I would do this for the other 5 people in the class. But what would be a problem would be, suppose I turn this in. The registrar would ask, say, what's Chase's grade? Well, it's like, I didn't want to give Chase a grade.
Mine was too high for the scale.
Okay.
It's like, well, was Chase in your class? Well, yes. Well, what's his grade?
Nothing.
I didn't want to give him a grade. That's not allowed. For every element in the first set, have to assign one and only one. So I can't just decide not to give Chase a grade. Now we do, on that particular one, modify things a little bit because sometimes we'll just decide, let's take him out of the domain. He really wasn't in the class. Let's get him off the roster. And Certainly, if I didn't turn in a grade, that might be one of the things the registrar would ask. Was he really in the class? Because if not, we need to fix something. And the fixing may not be that, oh, he needs a grade. It may be we need to get him out of the domain.
Or maybe just throw an F in there and call it good.
That could be too. But that's a problem. An input that doesn't get paired with anything. The other thing that's a problem, and I'm going to pick on Preston rather than my two Josephs, because that just... This also poses a problem. If there's, I don't even think I can do this with a grading, but if I turned in an A and a C for Preston, the registrar would call and say, which grade do you want to give Preston? Well, I want to give you both. It's like, no, he gets one grade. He gets one and only one grade. I cannot assign Preston 2 grades. So, that's by far a bigger problem with the function. I mean, if we want to pair an input with more than one output, there are ways we can do that. It just is not a function. It's something else. We want to look at functions. Now, notice in this, I do not have to give everybody a different grade. And in fact, here I cannot. There are only 5 grades. There are 8 of you. 7 here today, but 8 total students in the class. I cannot give everybody a different grade. There's also nothing that says I have to use all the grades. Those are both kind of ideas we'll pursue a little bit more. But in terms of just being a function, every input, so we'll also think of this in terms of inputs, every input has to go to one and only one output. And they have to be in the codomain. I can't just make up another grade, so I couldn't just for Chase, I want to give him a Q. Well,
Oh man, but I want a Q now.
yeah.
How poorly would I have to do?
Or how many comments do you make?
Yeah. To get a Q, I don't know.
Inquisitive.
Negative 12.
Yeah. Trying to think of another grade. If I'm going to make up a grade, you know,
Can
E
choose something.
expelled or something, you know.
That's a rough grade. I don't want that one. Spent a lot of money.
Quit coming, something. But you know, I can't make up grades. There are only certain grades I can use. Those are defined, but I have to give one and only one. So I think that kind of illustrates the 2 key things that are necessary to be a function. The other function I like to use is what I call the sheep-goat function. I believe it's in Matthew. And now we are not talking about what we did Wednesday.
It's going to go down in history. This conversation.
In Matthew, Jesus likens judgment to separating sheep from goats. Every person's going to come. So everybody's in set A. There will be a sheep-goat function applied. Everyone will be assigned either sheep or goat. Nobody's going to come and say, well, this is odd, you're on both lists. You're both a sheep and a goat. It's not going to happen. Neither is going to show, so, you know, anybody come and say, oh, this is odd, you're not on either list. You know, it's kind of like turning in a grade, not turning in a grade for Chase. Well, you know, there will be a grade assigned. If we think of sheep-goat as a grade assigned, it'll be one or the other, and it will not be both. So, that's a function. Now, even though as we sort of define the function, the idea is you tell me the input and I figure out the output. For a number of functions, we reverse that role. Most of you, as I was doing this, were thinking, I know what grade I want. And probably even beginning to think, if I want that grade, what do I need to be doing so that when he applies the gradebook function, I get the grade I want? That's a very natural thing for students to do. I hope you've also given serious consideration to that function when that day comes. Which do you want to be identified, a sheep or a goat? And given consideration, what are you going to do with Jesus' offer of salvation? Are you going to accept that or not? and do the other things. In the context of the scripture, there are other things mentioned, but certainly, are we going to accept that offer of salvation or not? Now, some other terminology that students will sometimes get mixed up with the definition of a function. But we'll be looking at functions that are referred to as one-to-one. A function is one-to-one if different inputs produce different outputs, always. Which both of the examples I gave, they cannot be one-to-one. There are too many inputs to give them all a different output. I have to repeat some grades. But if we start thinking more abstractly, different producing different, it's really tough to think about. I mean, there are lots of ways things can be different. So being different really isn't all that helpful. So typically for one-to-one, we use the alternative sort of definition, what's known as the contrapositive, that if f of, say, a1 equals f of a2, then a1 equals a2. If somehow we have ended up at what appears to be the same output, and we can prove, in fact, we had the same input, always, then we've proven the function's one-to-one. Or if we're given a function that is one-to-one, if it's ever the case that we somehow have the same output, well, we know, in fact, we have the same input. And that's what being one-to-one means for us. The other thing we can talk about is what's known as onto. Each possible output is actually achieved. And in fact, we call the range of our function the set of actual outputs. In terms of the gradebook function, I think you're all hoping the gradebook function is not onto. Because that means somebody's getting an F, somebody's getting a D. I guess you could be optimistic. I mean, somebody's getting an A if the gradebook function's onto, but let's say, Krista, you're the one getting the A?
Of course.
Okay. But as I said, it's not one-to-one. I'm going to have to repeat something. But depending on the function, these are different criteria. And up to this point, a lot of our work probably has been focused on the rule itself. Is the rule itself one-to-one, or is the rule itself onto? Part of the function idea, though, is we are going from some set to some other set. And we're going to be interested in, well, what if we start modifying the set? So suppose our function is f of x equals x squared, and we're going to go, in this case, from the reals to the reals. So we're allowing inputs of reals, we are allowing outputs of reals. Every x we pick, there's only one output, so it really is a function. Do we get any repeated outputs? I see some, at least one head saying no.
-1 and 1.
Okay, so -1 and 1 both go to 1.
Yep.
So we actually do get a repeated output. 1 comes from two different places. That's enough. Different inputs produce different outputs. So in a particular example, this idea is not, I mean, it is useful. It's not a problem necessarily. We can find two different inputs that actually give us the same output. And so it's not 1 to 1. So this one's not 1 to 1 because f of negative 1 equals f of 1. What about onto? Okay. Onto, we've got to achieve every possible output, so we're going to say now, what output are we missing? Okay. That we are missing. So it's not onto. F of x is never negative 1. And I guess a variety of ways we could say that, but we never get an output of negative 1. Well, what changes in this situation if I now go, say, from the reals to the positive reals and 0? So I'm not changing the rule per se, but in the language we're using here, I have changed the function because I'm using different sets. So does my changing of the sets do anything about what we said about 1 to 1? Yeah, still not 1 to 1 because we still have two different inputs going to the same output. What about onto? Since we changed the set of possible outputs, do we actually get all the possible outputs? And we do. So one of the things we're going to do here is kind of expand our idea of function. It's not just the rule. The set where the set of possible inputs, the set of possible outputs is part of what's building this function. We need to consider all of it before we make the decision on whether it's 1 to 1 or whether it's onto. Let me make one other change. Suppose we go now from the set of positive reals including 0 to the set of positive reals including 0. I mean, the reals are fractions n pi and square root of 2 and all decimals. Actually, if it were just fractions, no, let me look at that next, just what happens if it say where the fractions and fractions.
Doesn't it still work though, because the odd numbers only can be made by multiplying two odd numbers together? Is anything times an even number? Oh, it's a positive, not odd, never mind.
Yes. And it's also the reals. I think you may have been thinking integers. I mean, because odd is usually not something we talk about in relation to the integers. You know, it's odd or excuse me, in terms of the reals. We talk about odd integers, even integers. I'm not sure I know what an odd real number is.
No, I was just assuming anything that ended with an odd number. That's just my thought brain working right now.
Okay. So, is this 1 to 1 or not? Do we get any repeated outputs now that we've changed the domain a little bit? Right. We never get any repeated outputs. This now is 1 to 1. And it is also onto. We actually get all the possible outputs, only now we're getting them from just one place. And in fact, if we've got a function that is 1 to 1 and onto, that's exactly the type of function where we could reverse the process. Here's the answer, and we know exactly where it came from. Because it does come from somewhere, and it comes from only one place. And that's what we do in terms of, say, the square root. That's why in the square root function we only get the positive answer, not the negative, because there's just the convention that for the square root, we already made this restriction on the domain. So we are only getting the positive answer out when we take the square root. Other terms that are sometimes used on this, I tend to forget. Let's see. Onto, I think it's also called a surjection in some books. One-to-one is called an injection. And if it happens to be both, it's called a bijection. You're not doing your sport back there, are you, Joseph? No, you're not. Oh, okay.
On-to function PowerPoint.
That's some serious click, click, click. No, you better not be playing League of Legends back
We
there.
need way more mouse clicking.
Oh, way more mouse clicking in that case? Okay.
Probably some solid like lettering.
Okay. Now, suppose we had two functions. F and G. So F is a function from A to B, and G is a function from B to C. We could build the composition G composed with F, which goes from A to C. And one way to kind of think of this is, we've got the three sets A, B, and C. F takes an input from the A set and sends it to an output in the B set. G then takes that output onto something in the C set. And so we've got kind of a two-step process, G of F of X. Or we could look at it as a one-step process, starting in A and jumping immediately to C. And in life, a lot of our complicated tasks, as you're first learning them, you break them down into the simple tasks. You do this first, then you do this, then you do this. Whereas as you get more experience with that, you just do the one step. Learning how to drive. Get in, fasten your seatbelt, adjust your mirrors, start the car. But there's sort of a checklist. Do this, then this, then this, then this. And then later you get in and go. Hopefully remember to do all those things. Maybe not adjust the mirror quite as much because if you're the only one driving the car, why should it have moved? But there's some things with that, but we do just one step. Well, let's team this idea up with our ideas of one-to-one and onto and begin to think of some questions that are now much more abstract and relate to proof. So suppose we were asked to prove the following statement. If G composed with F is one-to-one, then F is one-to-one. And I didn't state it here, but sort of hidden in this would be the assumptions that the domain and codomain are right, that this composition makes sense. That F, say, is going from A to B. G then would have to be going from B to C. And G composed with F then is going from A to C. I think that's the domain and codomain. But here our challenge is that we don't really know what the function A, B, and C look like. or excuse me, the sets A, B, and C. There are sets A, B, and C that we're working with. We just don't know what they look like. And we have these two rules, F and G. And we don't know what they look like. But we are told that the composition G with F is 1 to 1, and we are asked to prove that F is 1 to 1. Well, again, we encounter here our word that we're going to encounter repeatedly through advanced calculus, prove. I mean, in calculus we use lots of results. In advanced calculus a lot of times it will be, can we prove that result? Now, why is it true? So, we're being asked, prove that this is actually the case. And so we've got to kind of definitely take a step back and, okay, what am I really going to have to do here? Well, if we look at the conclusion, where are we headed? Where we want to get is we need to show F is 1 to 1. That's what we're being asked to do. Well, how exactly do we show something is 1 to 1? We will need to show that if somehow F of A1 equals F of A2, then A1 equals A2. So ultimately, that's what we're going to have to do. So if we begin to think of how the proof is going to look, we'll be starting with, suppose F of A1 equals F of A2, and where we're headed toward is we need A1 equal to A2. And if we can do this, we could say, well, this tells us F is 1 to 1. And probably I'll switch to that notation more than the 1 to 1 in words. So.
This suppose, are we getting that basically from our assumption if?
Our assumption if here,
If there, okay.
on what do we need to show that the function is 1 to 1? A function is 1 to 1 if, whenever we're sort of sifting through everything, we somehow happen on two outputs that are the same. Can we prove that the inputs had to be the same?
Okay.
So we're sorting through all the F outputs, and we suppose we find two that are the same. What it takes, the mathematical standard of proving something is 1 to 1 is if we ever come up with two outputs are the same, two outputs of a function F that are the same, and we can show the inputs, in fact, have to be the same. Not just could be or might be, they have to be the same. We can do that without any other information other than we've got this function that somehow we had this two same outputs. That's what it takes to show the function's 1 to 1. So that's what we're going to have to do to show that it's 1 to 1. And that's part of our process of proof is to figure out, okay, what exactly do I need to show? Because, I mean, showing it's 1 to 1 is a bit nebulous. I mean, at least now we've got something maybe a little bit more familiar. Now, we know what equality looks like. We've got two outputs that are the same. We want to come up and figure out that the inputs have to be the same. We're still very much left with a challenge because we can't just say, I'm going to cancel the F's because we don't know anything about F. That's not going to work for us. And if we could just cancel the F, then every function would be 1 to 1. Or x squared could have been even when we had f of 2 equals f of negative 2. If you could just cancel the f's, then 2 has to equal negative 2. So it's only special kinds of functions where that work, and that's what we're trying to do here, is do we have that special kind of function where ending up at the same place is only possible if we can conclude we had to start at the same place. If that's what we can conclude, we have a 1-to-1 function. So, very rough sketch of our proof here. Big hole kind of in the middle. But at least we have a place to start, and we kind of know where we're headed. We want to get the two, A1 and A2 equal. Well, we analyzed our conclusion. What's it really going to take to prove this? And what do we need to prove? What does that really mean? And that's something we'll do fairly often. Identify exactly what are we trying to prove, and is there some other way we could say that might be a little bit more helpful to us. So we've done that here. The next thing we need to figure out is, okay, what am I assuming? I do have an if here. So we are assuming G composed with F is 1 to 1. Which means we know, or we're assuming in this case, but we know that if G composed with F of some input equals G composed with F of some different input, for this mapping, since it is 1 to 1, we know the inputs had to be the same. Now, with a lot of problems involving composition, there are times it's helpful to think of it as a one-step process, other times maybe as a two-step, and be more specific about what the two steps are. So if we do that here, remember G composed with F is G of F of whatever the input was. So we're still kind of brainstorming. What does it mean for the composition to be 1 to 1? What exactly do we mean by G composed with F? And we're hoping for some aha moment or something that we can at least think about and try. So as we look at this,
Can you use them both?
can we
Can you
use,
use both the definitions of G of F?
I suppose, in what way are you thinking?
Well, one, you can conclude that F of A1 equals F of A2, and then the other you conclude A1 equals A2. Can't you? No.
I'm not just totally convinced about either one of those, because in a sense we're not interested in concluding that F of A1 equals F of A2. In fact, that's really kind of where we're starting our proof. We do want to get A1 equals A2. And there is a way we can conclude that at this point. Okay, let me, I guess. Don't change the second. So there is a way we can conclude that, but we have to know something else to make that conclusion. And in our original sketch, G's not in there anywhere. But what we know is something that involves G. So it would appear as we kind of look at this, we need to get G in there somewhere. What are you thinking?
I don't know if this would help, but since we've got F of A1 equals F of A2, and we've got that inside that function, could you substitute like an X or something in there? And then you can have G of X equals G of X? Because we're supposing F of A1 equals F of A2. Could you call that a variable or something?
How
Because
is
F
that
of
know.
A1 and F of A2 are both elements of set B.
Yeah, we could, I suppose.
So then don't we know already that G is 1 to 1? And doesn't that help us move closer to realizing that as well?
Actually, I don't know that we know much of anything about G, and nor are we all that interested in figuring out anything about G.
Okay.
We know the composition is 1-to-1, but I don't know that we know that G has to be. In fact, if we can get this proven in the next 4 or 5 minutes, I can come up with an example where G does not have to be 1-to-1, and this still holds. That the composition might be 1-to-1 even if G is not. So that is part of our challenge, is to only use the things that we know. And to try to figure out, okay, well, what might be helpful? Now, you were saying, could we let X be, say, f of A1? And I guess we could, but I need G in here somewhere. If I take G of this side and G of this side, do I know anything about those two?
We know they're equal,
Yeah, how do we know they're equal?
because we know f of A1 equals f of A2 from the next line above. And so G of the same number is gonna be equal G of the same number.
Yeah, each input produces exactly one output. G is a function, so once we have an input, we have two different names for the same input, but there's only one output that we get when G is applied to an input. Just the fact that it has two different names doesn't change the fact that it's the same input. G of that is the same result. So we know it's equal since G is a function. And I might add, at some point in graduate school, my thesis advisor began to stress on me the fact that mathematics need to be written in complete sentences, which is a totally foreign concept to an undergraduate student, and it was to me as a graduate student as well. What do you mean? Can't I just say equals and do this and write out a little reason by the side? And he was like, no, you really can't. So that was quite a learning curve. A proof is a communication, and so how do we write it beyond even just the words that we're thinking? And because I'm saying a few things here. How do we try to get all that information down so that it's clearly communicating to anyone who would pick it up and read it? And that is a challenge. So in fact, I suppose we ought to put, suppose f of A1 equals f of A2. Since G is a function, G of any input only produces one output. So the fact that we have two different names for the same input, we're still going to get the same output of G in this case. Okay. Does that help us? Do we know anything about G of f of A1 and G of f of A2? Do we know anything if they're equal?
Yes.
A1 equals A2.
A1 equals A2. That left way too much space. So, we know this since G composed with F is 1-to-1. And that was what we were hoping to get. And so the proof actually ended up, I think, a lot shorter than we were probably thought it was going to have to be, but there was one key step we had to kind of realize in there that since we knew something about G composed with F, somehow we had to get G in here. But we don't know anything about whether G is 1-to-1 or not. We just know something about the composition. But if we take G of both sides, we now have a composition. We do know something about the composition. In fact, the something we know is extremely helpful for us. Now, we were thinking, well, doesn't G have to be 1-to-1? So let me see if I can come up with an example where no, it does not. So suppose f of x is a function from, say, the positive reals to the positive reals. Or in fact, let's just say to the reals. And then g is a function from the reals to the reals. So the composition g composed with f is going to go from the positive reals to the reals. And let's just suppose f of x is, I don't know, 2x. G of x is x squared, and so the composition g composed with f is 2x quantity squared. Or I suppose if we simplify it out a little bit, 4x squared. Notice, because of the domain that we end up with here, g composed with f is 1 to 1. We do not get any repeated outputs from this because we're only using positive inputs. Whereas g does give us repeated outputs. It just happens the way the function runs through here. F doesn't ever give us inputs where g would repeat. So in the composition we have 1 to 1. Notice g does not have to be, but we just proved, well, f's going to have to be. If this composition ends up being 1 to 1, the first step is going to have to be 1 to 1. The second step will not have to be 1 to 1. And that's essentially what we proved here. But we did it in general, not with specific examples. And our challenge is, with things done in general, is can we think about the general principles that are going on here? What do we have to do in general to prove this is true? Because we have no specifics to dive in and really start working with and experimenting with anything specific. None of that's there. And if we start thinking of specific things, we will probably miss some of the generality that was intended with the way the problem was posed in the first place. So knowing something about the composition does tell us something about at least one of the pieces, but it's not always necessarily the piece we might think. And it certainly in this case didn't tell us anything about both pieces. You know, G could be 1 to 1, it might not be. We really have no way of knowing. In the abstract, there are certainly examples we can come up with where that second step isn't 1 to 1, but from first to third still ends up being 1 to 1. And if that happens, well, the first jump has to be 1 to 1. Okay. Well, we're got 4 minutes left, but I'm not sure in 4 minutes we're going to accomplish anything. There is some induction in the appendix as well. I need to refresh my memory on whether I try to do that right now or wait a little bit. We will review induction at some point. I just don't remember if I try to do it right now or a little bit later in the course. So I'll try to figure that out by Monday. And we will pick up on Monday either with induction or jump to section 1, 1.1.